Welcome. Dear students, today we are going to discuss about SN2 mechanism, SN2 reaction. SN2 reaction is a type of nucleophilic substitution reaction. And which organic compounds show nucleophilic substitution reaction? Yes, alkyl halides. So as I said earlier, alkyl halides, they show nucleophilic substitution reaction, and this nucleophilic substitution reaction can proceed through any of the two mechanisms. Either it can be SN1 mechanism or it can proceed through the SN2 mechanism. In this class we will study what is nucleophilic substitution reaction, and also we will look into what is SN2 reaction. So let us first discuss about nucleophilic substitution reaction. Nucleophilic substitution reaction. Which organic compounds show it? Alkyl halides. So I take the simplest of alkyl halide here. Consider methyl bromide and consider OH minus. What would be the outcome of the reaction? To predict what would be the outcome of the reaction, we have to study the nature of the reactants that are involved. OH minus has a negative sign over it, therefore it is a nucleophile. Correct? It's a nucleophile. Take the case of CH3Br. CH3Br is a polar organic compound. Polar organic compound means that it is having a dipole system in it. Dipole system means that one end of it is positive and the other end of the molecule is negative. So this molecule is bound to dissociate, and what would happen? Br minus would get released. And what would result here? CH3 plus. That CH3 plus OH minus comes and attacks. So methanol results. What has happened in this reaction? Which is the nucleophile? OH is the nucleophile, and what has it done? It has done the substitution. It has substituted another nucleophile. So therefore nucleophilic substitution reaction. So this is what is nucleophilic substitution reaction. Now let us come to specifically what is SN2 mechanism. Okay, nucleophilic substitution reaction, as I discussed, it can proceed through two ways, SN1 and SN2 mechanism. Let us now study what is SN2 mechanism. SN2 mechanism. So what is the full form of SN2 mechanism? SN2. What is the full form of SN2? Let's reverse it. We have to reverse read. Bimolecular nucleophilic substitution reaction. Bimolecular nucleophilic substitution reaction. Nucleophilic substitution reaction. Okay. So bimolecular, that's the most important word. Bimolecular. That means two molecules are involved. If two molecules are involved, what would happen between them? If in a reaction two molecules are involved, then what would be the probable mechanism of action of reaction? Yes, it will be collision. So these two molecules are colliding with each other. Which two molecules? Alkyl halide and nucleophile, right? So they are colliding with each other. Dear students, when I was teaching today in the class, I told to my students that if in this classroom I lock two students, one the nucleophile and the other the substrate, it would take a long time for both of them to collide with each other. The rate of collision will be very, very long. If I am putting 60 students, that is my class strength, if I am putting 60 students into this classroom and I consider the classroom as a test tube and I divide it into 30 and 30, 30 being nucleophile and 30 being the substrate, then the chances and the rate of collision of all of them will increase. Now if I pack the whole college into that classroom and if I divide them into two equal portions. One half is nucleophile and the other half the substrate, then the rate of collision will be much higher. So in a bimolecular reaction, where collision is involved between two molecules, the rate depends upon what two things? The two things itself, that is how much the substrate is there and how much the nucleophile is there. That is, the rate would depend upon concentration of the substrate and the concentration of the nucleophile. So that is SN2 basic information. To understand SN2 much better, we will look into the mechanism. We will draw structures and look into the mechanism. So this is our nucleophile, which is OH minus, and this is our alkyl halide, which is the substrate, and here is the bromine. A tetrahedral shape is given here. Now, as we know, OH is the nucleophile. The Br, this is a polar organic compound. That means there is a dipole in it. This side, dipole means one side of this molecule is negative, the other side is positive. Now, the carbon is positive in nature. Nucleophile gets attracted to this side, right? It will get attracted to this side, and what would happen? A transition state will come in between. In this transition state, note how I am writing OH. So this transition kind of state would result. This is the transition state that looks like the spokes of a wheel. Spokes of a wheel. We have seen bicycle wheel, how the spokes, they are arranged themselves, the atoms are arranged in the same manner like the spokes of a wheel. Such is the transition state. And what is the outcome? So this is the outcome of this reaction. So this is the outcome. So this is, I said this is the nucleophile. This is a polar organic compound. There is dipole in it. The side which is positive attracts OH minus. In the a transition state is formed in which COH bond is partially formed and CBr bond is partially broken. Okay, Br has not left nor has OH entered. They are doing it simultaneously. OH is entering simultaneously and Br is getting ejected simultaneously. This bond is partially formed and this bond is partially broken, and at last what would happen? The Br bond will be, CBr bond will be completely broken and COH bond will be completely formed. COH bond will be completely formed. So this is the SN2 reactions mechanism. Now let us discuss about the orientation of SN2 mechanism. What do we mean by orientation? What we mean by orientation is where the incoming group will be directed to. This incoming group, where it will get attached. That is called as orientation. That is what we mean by orientation. So here, as you can see, the Br has not completely left the carbon, correct? It has not completely left, it is still here. So if the OH wants to attack from here, it can't, because there is already another nucleophile. In fact, OH may get repelled by this nucleophile because both are negative in charge. The only option that is left with this nucleophile, that is OH minus, is to attack it from the backside. There is no other option. It has to attack it from the backside. And when it attacks from the backside, as we said earlier, partial bond is formed, COH bond is partially formed and CBr bond is partially broken, and we get a transition state like spokes of a wheel. And finally, what we get is this kind of product, which is actually inverted product, right? This is inverted. Look at the configuration, how these atoms are lying. Look at these H, how these H have got inverted. Look at this nucleophile, how this nucleophile got inverted. An inversion of 180 degree has occurred here. Such type of inversion, this type of inversion is referred to as Walden inversion. What it is referred to as? Walden inversion. So we get a product of inverted configuration or inverted product we get in SN2 reaction. Dear students, now we have discussed about reaction, mechanism and orientation. Let us now discuss about reactivity. Reactivity. So by reactivity, what do we mean? What we mean to say by reactivity is which alkyl halide will react by SN2 mechanism. We know nucleophilic substitution reaction is shown by alkyl halide. Now by SN2 mechanism, we want to know by SN2 mechanism which alkyl halide would react. Whether it will be your primary alkyl halide, whether it will be secondary alkyl halide, or whether it will be your tertiary alkyl halide. Tertiary alkyl halide. Which of these has a higher probability to react by SN1 mechanism? This is primary, this is secondary and this is tertiary. Which of this has a higher probability to react by to choose the SN1 mechanism? For this we have to compare, to know this, to know the answer, which of this alkyl halide would undergo SN1 mechanism. To know this answer, we have to go for comparing the carbocations. Let us compare primary carbocation with secondary carbocation and tertiary carbocation. Let us compare the carbocations. This is the primary carbocation. This is the secondary carbocation, which I am going to draw now. And this is the tertiary carbocation. Which of these carbocations is more stable? This is primary, secondary, tertiary. Which of these carbocation is more stable? Do you know? Do you have an answer? Yes. The tertiary carbocation is the most stable of all carbocations. Why? Because these R groups, they can pump their electron to this carbon, right? And thus these R groups can efficiently distribute their electrons to this area. And here the density of positive charge would be very less. Here also it is pumping the density and it is pumping its electron here. The density becomes less, but not as less as this. Here also there is pumping, but the pumping is only from one side. Here also it becomes less, but the pumping is much less. The decrease in the positive charge is much less compared to this and very much less compared to this. So the most stable, where this positive charge is the least, that is the most stable, and that one is a tertiary carbocation. And the most unstable of it is the primary carbocation, because the positive charge here is not greatly reduced. So the primary carbocation is the most unstable of all carbocations. Now primary carbocations come from which alkyl halides? Yes, it comes from primary alkyl halide. Okay, so the primary alkyl halide would never want to become a primary carbocation, because the primary carbocation is actually unstable. So the primary alkyl halide, it will always undergo SN2 reaction, because in SN2 reaction, one need not form carbocation. Carbocation should not be formed, right? Collision should take place simultaneously. Like when Br was here, OH should attack from backside, correct? So that is a condition of SN2 reaction. A carbocation should never get formed, otherwise OH will attack from this side only, front side only. So to fulfill the SN2 conditions, as to see the SN2 condition, a primary alkyl halide will undergo SN2 reaction, because a primary alkyl halide's carbocation is the most unstable, and actually it won't become any primary carbocation, and SN2 reaction doesn't need the formation of primary carbocation. Therefore, primary alkyl halide will undergo SN2 reaction. Now there is another aspect also. There is another thing that is to be seen, which is stereochemistry of alkyl halides. Stereochemistry of alkyl halides. So we will see primary alkyl halide here. This is primary alkyl halide. Sterical hindrance of carbocation of alkyl halides. This is the primary alkyl halide. Now I am going to draw secondary alkyl halide. And now I am going to draw the tertiary alkyl halide. Now in tertiary alkyl halide, the groups are very much bulky, right? In secondary alkyl halide also there are bulky groups. These are all bulky groups, that is CH3. And in primary alkyl halide, bulky group is there is only one bulky group. In tertiary alkyl halide there are 3 bulky groups. Now if OH minus, that is the nucleophile, how can it attack a tertiary? From where will it attack the tertiary alkyl halide's carbon? It has to attack this carbon. How will it attack? How will an OH minus attack this? It is very difficult to attack this carbon, but it is very easy to attack this carbon, because there is no steric hindrance in primary alkyl halide. So therefore collision can comfortably take place in a primary alkyl halide. So therefore primary alkyl halide will undergo SN2 reaction, because that is what requires a collision. So therefore primary alkyl halide will undergo SN2 reaction. Dear students, we have seen that why primary alkyl halides undergo SN2 reaction very easily, comfortably. Number one factor is stability of carbocation. A primary alkyl halide's carbocation, that is a primary carbocation, is very unstable. So therefore a primary alkyl halide would never want to become a primary carbocation. And actually SN2 reaction doesn't need the formation of a carbocation. Okay, a carbocation should not be formed. So therefore SN2 primary alkyl halide show SN2 reaction. And also we have seen stereochemistry, where primary alkyl halide has more space so that collision can take place. So these are the 2 factors that favor SN2 reaction for a primary alkyl halide. Dear students, I hope you liked and enjoyed the class. If you have done so, please do not forget to subscribe the channel. Thank you very much.